this bromine, which is going to pull electron density away, which pulls electron density away from this. So it's either at the high end of that, or sometimes they creep up into, like this one, creeped up into other areas because of the electron density being pulled. You can see that too. So if it's just outside your normal region, and you have an electronegative atom close by, that makes sense. Okay? And then the further away you get, the less of an effect. So something way out here is definitely not being affected, not really affected, maybe affected a tiny bit, starting to get affected, and really affected. Okay? Just how we move our electron, how we move our chemical shift down based on electron density. Okay. Other questions? Because it's long to make. 35 minutes. Okay. 4 is the hardest. You want me to do 4 or you want me to do 5? You're probably going to get through both of them. 4. Okay. All right. You're not going to like 4. But 4 is rough. Okay, so we start off not so good where we can't even see the Fahrenheit, right? So we got a hint. It's up here. Looks like maybe 230, 230, 232, 234. That's why it says hints, okay? So 235, 6, 7, somewhere in there. 230, let's say 235 to 238, somewhere. Okay. Is that okay? Then we have an amorphous. It's not great. I mean, it's better if we don't, but we do have the percent composition in there. So we can use that to narrow down our possibilities. If you go through and you figure out how many nitrogens you have with any of those numbers, it's really close to 2. Okay, so 2 tells you it's an even number, which tells you your even number of nitrogens, therefore your molecular weight must be even number. Okay, so you can eliminate anything out of that thing. So we said 235 to 238. So we got 236 or 238 in here as our possibilities. And once again, continue to work through your thing, and you figure out how many hydrogens you have, or carbons, etc., based on. Does that make sense? Yeah. Okay. So without the percent count, you're really screwed, and you have to then use the integrations on your. You have to use integrations on your proton NMR to figure out the exact number of hydrogens. So if you come up with something and it's still looking a little dicey, check that. That's another place you can find it. So let me just pull that up and show you. If we count this up, okay, it should come out to be around 20 on the system. But if you count this, it's 1, 2, 3, 4, 5, 6, 7, 10. 10 is not around 20. Oh, sorry, 10. You try to do this. This is opposite. It's harder than you think. We got 10, but we're supposed to be somewhere around 19, 20, 21. Huh? What? Stop. Yeah. That's the you get a 0. You get this problem off. What's going on? Multiply by 2. Remember, these are ratios. The ratios. It's a ratio. So when you do an integration, the computer does not know what your molecule is, right? It's just analyzing the data that's produced with these peaks, and it's taking the area under each peak. And we relatively set it. Now you guys get lucky because we cheat and we said, hey, this is probably an aldehyde proton, or it's not. So you can cheat and find hydrogens that you know what they are and set it equal to that, and then everything becomes relative. Okay. This one, I think they went through and said, well, what's my smallest number, and set it equal to 1. Okay, because they didn't know what anything was. So we're like, we start there, we know at least we have the baseline, and it might be 2 times, or 3 times, or 6 times, or 8 times, or whatever, but we have our baseline. Okay, make sense to everyone? Okay, so working our mass spec together gets us close to the number of hydrogens. We can confirm from here, and then we've also made our lives easier because we instantly figured out that everything needs to be doubled to equal the number of hydrogens in our system. Good so far? Oh, this one's hard. We haven't got past the formula yet. We're already struggling. Okay. Notice I haven't looked at any of these things for like chlorine with goalposts, or bromine with goalposts, or chlorine with 3 to 1, paranine on +2. It's because we have our percent comp and there's been no percent X in any of them, right? So I don't have to try to pay attention to that because I know there's not any there. So really it's just getting my paranine so I can get my molecular form. Okay, so for number 4, we got C13, H20, O2, N2, even number of nitrogens on that with even molecular weight. Our molecular weight is actually 236 on that system. Okay, so our UUs are 13 minus 20 halves plus 2 halves plus 1. So 13 minus 10 is 3, plus 1 is 4, plus 1 is 5. Okay, so I have 5 units on saturation, which means I'm looking for benzene, and I'm looking for a double bond or an additional ring of some type. Okay, so far so good. Okay, bullet line iron. Okay, so I got stuff way up here that I don't usually see things. All right, so what is that most likely? NH or OH, and what is it definitely not? OH. Okay, so that's kind of the counter. Not as broad as we usually see it, but it actually is because we'll find it's attached to the ring, and that helps kind of sharpen those things up. But don't go down that rabbit hole. All right, so NH2 there, and then we got our sp3 below. That's kind of high, but there could be some funkiness with all these nitrogens and things that are going in there. So I'm not really going to worry about what that extra peak is. I know I at least have an NH2, and then I have some sp3, and then we'll go from there to see what else we got. Okay. Over here, we got what looks to be a carbonyl at just below 1700. It could be a double bond, though, as well, right? So we got to leave both of those open as either carbonyl or double bond. And then at 1600 and 1500, we have benzene, even though we don't have fringing. We said we were trying to look for benzene. That is reasonable. We can try to confirm it through our proton and carbon as well. All right, with me so far.
How did you know the NH2 was together and not like 2 separate NHs?
So you don't. Yeah, you don't yet. So where you would look for that, remember we said OHs and NHs don't split, and then they're tend to be broader. So if we actually go into our proton NMR, and I know it's not the prettiest one here, this guy, and they can come anywhere in chemical shift. They usually are in the middle, but they literally can come anywhere based on hydrogen bonding. This is our broad non-split thing, so everyone else has splitting listed, and they don't have anything. So this is your 2H, because we doubled everything, peak. So we have an NH2 group from you see the next one? Yeah, kind of sharp these things are. Right here? Yeah, that's the splitting too. So you can't have splitting. They're not going to split. They're not going to split other peaks. So they're not going to split. Correct. Okay. What am I doing? Okay. So far, so good. Yes. So we have pieces that we've kind of found from our IR and kind of confirmed is a benzene. We have a NH2 that we worked through to confirm. We haven't conclusively said we have a carbonyl yet, as opposed to an alkene. Let's look at our carbon NMR. That might help us. There to start with. Okay, there's our carbon NMR right here. Okay, so we have peak up here at this is the part one. Yeah, okay. At 167-ish or something, that's going to be a carbonyl. And that 165 to 220 are carbonyls, and then the 160 to 165 to 180, 160 to 185 is usually your acid or ester, and then the 190 to 220 is usually your aldehyde. Okay, go ahead, Marsh.
Is that too high to be a part of benzene?
It's depends on what's attached to benzene. So in theory, could it be part of the benzene? Yes. Okay. However, if you look at your benzene region in the proton, start here, 2H, 2H, those are the only peaks that you have in there, which is suggesting to us what? Paradise substitute, those often do look like doublets, even though they're not listed on here. 2H doublets, but we can confirm that because if it is paradise substituted in the carbon NMR, we would see what? 2 small, 2 really big. Okay? If we look at our carbon NMR, we got 2 small, the 2 really big. So this thing right here is our paradise substituted benzene, which leaves that out to be our carbon. And so we don't have another carbon to be part of a carbon double bond. Sound good? Okay, deductive reasoning, right? This one's super hard. I'm not even joking. This is mean. I'd never do anything that's like anything like this to you on an exam. But for practicing to really see where you can see things when it's confusing and how you can work pieces together and really grind, it's a great problem because it really strengthens a lot of skills as you're going forward. Okay. All right. Anyways, pyrimidine substituted benzene, and now we got a carbonyl, probably an ester, amide, something like that. We have both oxygen and nitrogen in here, so I don't want to eliminate one of the possibilities yet, but I know this isn't going to be a ketone or an aldehyde. Okay, makes sense? Yes? Okay, so ester or amide. So far, so good. Yeah. We're never going to make it through this one. Not with this. Okay. So back to the proton and carbon correlating together. Okay, so we got this whole part of our spectrum done right over here. So now we're working on this one. Trying to correlate. We have 1, 2, 3, 4 peaks over here. We have 1, 2, 3, 4, 5 peaks over here, but we already said that 1H peak there is or the 2H peak there, I should say, is our NH2 group, which leaves then our 4 and our 4. Okay, with me on that? Okay, so we have a 2H, 2H, 4H, 6H. Right? Is everything? Sorry. 2H, 2H, 4H, 6H. Let's double check. Okay. So what does that tell us we have? We have CH2, CH2, then we have 4H and 6H are going to be 2 equivalent CH2s, 2 equivalent CH3s. And if you look at this, this has that quartet for CH2 and our triplet for CH3, which we've seen many times now. Those are our so we have 2 equivalent ethyl groups in that system. Okay? So we might as well just go ahead and get that out of the way to begin with because of this. Okay? And then these CH2s can't be attached to anything that have hydrogens. Okay? With me? Okay, so I think I have all my pieces. Let me check. Okay, 6, 7, 8, 9, 10, 11. We're gonna. Oh, I had the other 2 CH2s tonight. Sorry. See, so why you check? So we had the CH2, CH2, and then the 2 CH2s and the 2 CH2s. Okay, so 6, 7, 8, 9, 10, 11, 12, 13 carbons. Our hydrogens are supposed to be 20, so there's 4, 6, and then this is 10 here, right? So 16, 18, 20. Okay, so we have all our hydrogens. 2 oxygens, we have 1 oxygen. So we're missing an oxygen. And 2 nitrogens, we have 1. So we're missing a nitrogen. Yeah? What's that? Yeah, this is rough. Okay, we're out of time, but so here are our pieces. Now we got to go back and forth and start saying, where do I see something that I can conclusively put together based on chemical shift and splitting? I'll put the key up for these. Okay. That makes sense to everyone? How I got to these pieces? Don't even tell me no. Okay. So getting this is the first big part, right? This is your big hurdle, is to get the pieces. Then you got to start micro putting in get bigger pieces. Go where it's easy first, then struggle, right? But if you can make big pieces, sometimes they just all fall in line. This one's not going to just all fall in line. You're going to have to explore different possibilities and then really reason it out based on splitting and chemical. Meh. Overrated.